Hello all, my name is Ashutosh Rastogi. I'm a teacher by profession. My mission is to impart quality education for all. For that purpose, I'm creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos.
Anyways, today in this particular lecture, we're going to discuss about PN sequence generation and its various properties. So these are the outlines. We'll start up with the introduction. Then we will going to discuss the block structure of PN sequence generator with the help of linear feedback shift registers. Then we're going to discuss various properties of PN sequences such as balance property, run property, and its autocorrelation property. So in our last lecture, we have briefly understood about the spread spectrum communication system. We have studied that the spectrum is expanded with the help of PN sequence generator. So obviously, for expanding our signal, we are achieving so many advantages such as our signal will become difficult to intercept. It will also difficult to jam. Apart from that, it could be easily hidden. These are some of the advantages that we have in our spread spectrum communication system. So this spreading would have been done with the help of PN sequence generator. So in this particular lecture, we'll try to study about how to generate PN sequence, and we're going to discuss some of the properties of PN sequences. This is the generalized block structure of linear feedback shift register to generate the PN sequence. So it is made up of linear feedback shift register. So in linear feedback shift registers, you will be having some registers such as these registers which are made up of flip-flop. So these flip-flop outputs will going to enter into a logic, and the input of this particular flip-flop is the linear combination of the previous states of the flip-flop. They all are supplied with the common clock. So what is so peculiar about linear feedback shift register? The special point about the linear feedback shift register is here the input to the flip-flop is the linear combination of the previous states of its register. That is why we are calling it linear feedback shift registers. And here we will getting some output sequences. So now we're going to discuss some of the specifications of PN sequence generator. The output sequence depends upon the number of shift registers M, initial states, and the feedback logic. This is quite clear as we have already seen in our last slide that it is containing M number of registers. So obviously the output sequence will going to depend upon those registers. Its initial state, what will the initial state of those registers, whether it is 0 or 1, and the feedback logic. So obviously the output sequence will going to depend on all these points. So for M flip-flop, the total number of state is 2 to the power M. Obviously, since flip-flop is a 1-bit storage device, so it could retain either 0 or 1. So obviously if there are M number of flip-flops, then total number of distinguished states will be equal to 2 to the power M. So the maximum length of the period of this sequence is n is equal to 2 to the power m minus 1. So after this period, the PN sequence will going to repeat out. So if the feedback logic only consists of modulo 2 adders or it is made up of XOR gates, then the initial state cannot be all 0 state. If all inputs to the flip-flop is 0, then it will going to produce 0 output, and overall it will not going to generate any new sequences. It will going to generate 0 0 0 in a continuous pattern. That is why we are saying that its initial state cannot be a 0 state. So the period of PN sequence produced by the linear feedback cannot exceed 2 to the power m minus 1, since after that period it will going to repeat out its own sequence. So when the period is exactly 2 to the power m minus 1, the PN sequence is called the maximum length sequence or M sequence. So this is also your maximum length sequence. So when the period value is equal to 2 to the power m minus 1, that is called its maximum length sequence, or we could say M sequence. Now we're going to discuss an example of PN random sequence where m is equal to 4, or we could say that we are using m number of flip-flops. So here we are using 4 number of flip-flops, x1, x2, x3 and x4. All would have been combined with a common clock, and the feedback path will going to have a modulo 2 sum of x3 and x4, and that will get feedback to the input of our x1. So this is the basic structure of LFSR for m is equal to 4, or we could say that when we are using 4 number of flip-flops or shift registers. So now we will going to see that how this LFSR will going to generate the sequence, or we could say the PN sequence. So this is the structure that we have seen in our last slide. So now we will try to discuss how it will going to generate the various sequences. So here we have made a table to calculate the outcome of PN sequence. So here x1, x2, x3, x4, these are representing the current state of the flip-flop, or we could say that the shift register. Here is the clock. So initially we are assuming that the present state of our flip-flops are 1, 0, 0 and 0. So as per this particular figure, what will going to happen is the input of x2 will be the output of x1, the input of x3 will be the output of x2, the input of x4 will be the output of x3, and the input of x1, it is nothing but it is the XOR of x3 and x4. So we have seen that basically the output values are shifting by one. That is why we are calling that linear feedback shift registers. So in the second clock, what will going to happen is this 1 will get shifted here, this 0 will get shifted here, and this 0 will get shifted over here. And the value of x1 is nothing but it is the XOR of x3 and x4. So when we're going to perform XOR operation between x3 and x4, that is 0 XOR with 0, the output will be 0. So this 0 will get over here. So what will going to happen in the third clock cycle is this 0 will going to come over here, this 1 will going to come over here, and this 0 will going to come over here. And what will the value of this x1 in the third clock cycle? It is the XOR of x3 and x4. So the XOR between 0 and 0, the output will be 0 and it will going to retain over here. So this is how we have calculated the various state values of different flip-flops. So in the fourth clock, we're going to have 1, 0, 0, 1. In the fifth clock, we're going to have 1, 1, 0, 0, and so on. So in the ninth clock cycle, we'll again going to have 1, 0, 1, 0, and again we're going to repeat the same thing. So this one will going to shift over here, this 0 will going to shift over here, this one will going to shift over here, and the input over here is the XOR of these two, 1, 0, that turns out to be 1. So the sequence will become 1, 1, 0, 1. So this is how we have calculated the different values of different states of flip-flops at several clocks. So we will going to have different values up to this 15th clock. At the 16th clock, we can say that 10000, it is again repeating out this our first sequence. So different outcome generated by this PN sequence generator is up to 15 clock only. As we can see that we are taking the output from this x4. So the output sequence of our PN sequence generator will be given by this 0, 0, 0, 1, 0, 0, 1, 1 and 0, 1, 0, 1, 1, 1, 1. We are not using this 0 since it is going to repeat it out. So up till here, this is the output of our PN random sequence generator. So since we are taking the output from the x4, as we had already said, hence the output of PN sequence generator will be 000, 100, 11, 0, 1, 0, tetra 1. So this is our 15-bit sequence, which is nothing but the outcome of our PN random sequence generator, as we discussed in our example. So whose length is 15. Obviously, when we will going to count out those states, that turns out to be 15. So here the PN random sequence generator length is 15. Or we could say that it is generating 15-bit length code as a PN sequence. So we need to map these sequences in the stream of -1 and +1 in order to modulate. So simple mapping would be looks like at the place of 0 we're going to use -1, and for 1 we are using +1. So after mapping, the output will going to looks like -1, -1, -1. For this one we have used +1, and for this 0 we have used -1. So this is the output of our PN sequence generator. So now we're going to discuss various properties of PN sequence. So number one is the balance property. So what is that? We're going to discuss it. This is actually showing the output of our PN random sequence generator as we have discussed in our example. So what we're going to do is we're going to calculate the number of plus ones. So we're going to count down. This is 1, here again +1, that is 2, 3, 4, 5, 6, 7, 8. So total number of +1 turns out to be 8, and total number of -1 turns out to be 7. So what balance property says that in each period the number of ones is always one more than the number of zeros. As we had already seen, we could also say that the number of +1 is always greater than number of zeros by 1. So in general, for a large value of maximum length sequence n, the probability of -1 is equal to the probability of +1. What do we mean by that? The probability of occurrence of +1 or the probability of occurrence of -1 will be equal when the maximum length sequence n will be large. So here also we could say that if we need to find out the probability of occurrence of +1, that turns out to be 8 upon 15, and the probability of occurrence of -1, that turns out to be 7 upon 15. So when this value of n is quite larger, then the ratio will become almost equivalent. That is why we are saying that for large value of maximum length sequence, the probability of getting -1 or +1 are equal. So the second property is the run property. Run is nothing but it is the string of continuous values. What do we mean by that? So this is the outcome of our PN random sequence generator. What do you mean by string of continuous value? We will going to count out -1, -1, -1. So this is a one run, then it is your +1. It is again a run of 1 bit, again -1, -1. In continuous fashion they came here. This is our third run, then +1, +1. This is also a continuous value of string. This is our fourth run, then -1. This is our fifth run, then again +1. This is our sixth run, then again -1. This is our seventh run, then +1, +1, +1, +1. This is again the continuous value string, and that is our eighth run. So I hope you understand what do we mean by the string of continuous values. So all those values which are same and coming in continuation, they are actually being called as the string of continuous values. So the total number of runs would have been given by n plus 1 upon 2. Here in this example, we have the value of n is equal to 15. So total number of runs turns out to be 15 plus 1 upon 2. That turns out to be 8. So when we're going to count the total number of runs, 1, 2, 3, 4, 5, 6, 7, 8. So this property also proves that the total number of runs is 8. So in general, the length of n bits can be given as, so run of length of n bits is equal to 1 upon 2 to the power n into total number of runs. So what do we mean by that? So basically we wanted to find out that how many number of runs are there in the complete number of runs which will going to have 3 bits, or we could say that how many number of runs in a complete run is having a 1-bit run, and so on. So suppose we need to find out the run of length 2 bits, that turns out to be 1 upon 2 to the power n, n is equal to 2. So 1 upon 4 times of total number of runs. So in our example, total number of runs are 8. So 8 upon 4, that turns out to be 2. So what this signifies is in total number of runs of 8, 2 number of runs are there which will going to have 2 number of bits. So here -1, -1, this is one run, and +1, +1, this is the second run. So there are 2 number of runs which will be having 2 number of bits. So this is the generalized formula in order to calculate the number of runs of length n in total number of runs. In order to calculate the run of length 1, Again, we have applied this formula 1 over 2 to the power 1 into 8, that turns out to be 4. What this signifies is in complete or total number of 8 runs, we will be having 4 runs which have 1 bit. So this is 1, 2, 3 and 4. So this also validates our formula. So now again the run of length 2 would have been calculated as 1 over 2 to the power 2 into 8, that turns out to be 2. So the total number of run of length 2 would have been calculated as this is 1, this is 2. So this is also validated through our formula. So run of length 3 would be equal to 1 over 2 to the power 3 into 8, that turns out to be 1. So here we can see that this is the 1 run. So in general, you could say that run property states that half of the sequence has 1 run, 1 upon 4th of the sequence has the 2 runs, and 1 upon 8th sequences has the 3 runs, and so on. So now we're going to discuss another property of PN sequence, that is autocorrelation property. So autocorrelation function of PN sequence would have been given as R of D is equal to 1 over n, summation starts from n is equal to 0 to capital N, Cn, C of n minus D. Here D represents the shifting. How much shifting we are performing, that is given by this D. So where n is the length of PN sequence, we had already mentioned. D is the shift in the sequence, and C of n is equal to plus minus 1. So C of n here signifies the individual value of PN code that is represented by plus minus 1. So for D is equal to 0, we have, if we need to calculate the autocorrelation function when shifting is 0, it would have been evaluated as R of 0 will be equal to 1 over n, summation starts from n is equal to 0 to n, C of n, and C of n minus D, at the place of D we have put 0, so we have again C of n. So after multiplying with it, the net outcome turns out to be 1 over n, summation n starts from 0 to n, C of n square. Since the value of Cn or the individual bit value that it could take is plus 1 or minus 1, so when we're going to multiply it, the outcome will be 1 only. So when we will going to evaluate this summation, what we are left with n times of 1 over n. So the outcome will be autocorrelation function at d is equal to 0 is equal to 1. So now for d is equal to 1, when we are going to calculate the autocorrelation function, it would have been calculated as R of 1 is equal to 1 upon n, summation n starts from 0 to n, Cn, C of n minus 1. So what is this value of C of n minus 1? As we had already mentioned that this D is representing shifting. So as it has been mentioned C of n minus 1, it means we could have this sequence C of n minus 1 when we're going to perform a single shift in the original PN sequence in Cn. So how we're going to calculate it is, we have Cn as minus 1 minus 1 minus 1. This is a sequence of our PN random sequence generation, and Cn would have been given by shifting the 1 to the Cn as, so C of n minus 1 will be, we have shifted one place on the right. So this minus 1 will come over here, this minus 1 come over here, and this minus 1 come over here, and so on. So at last this plus 1 will going to shift it back or feedback over here. So this is the sequence for C of n minus 1. So again, if we want to calculate C of n minus 2, then obviously what we will going to do is we have to perform cyclic shift 2 times. So Cn into C of n minus 1 would have been calculated as C of n sequence would have been written like this, and C of n minus 1 sequence would have been written like this. This is again a shifted version of this original PN sequence as we had discussed. So the value of Cn times of C of n minus 1 would have been calculated as minus 1 into plus 1, that turns out to be minus 1. Again minus 1 into minus 1, we have this plus 1. Minus 1 into minus 1, we again have plus 1. Plus 1 into minus 1, again we have minus 1. So this is how we have calculated this, the product term of Cn into Cn minus 1. So R of 1 would have been calculated as 1 over n, summation n starts from 0 to capital N, Cn into n minus 1. So we just have to sum this particular sequence. So what we are left with 1 over n times of minus 8 plus 7. So the value of capital N is 15 in our example. So the complete value would have been calculated as, or turns out to be, minus 1 over 15. So similarly, it can be shown that if we're going to calculate R2 or R3 or up to any value of R14, the outcome of autocorrelation function turns out to be minus 1 over n, or we could say that minus 1 over 15 as per our example. So in general, we can say that the autocorrelation of PN sequence can be given as autocorrelation function R of D will be equal to 1 when D is equal to 0 or shifting is equal to 0, and for D is not equal to 0, its value turns out to be minus 1 over n. Obviously, we are talking about only a single period. We can represent this relationship through a graph between autocorrelation function over the index value. So this would have been evaluated like this one. So this is actually our, over the x-axis we are showing the difference index values, or we could say that different values of n, and over y-axis we have plotted autocorrelation function. So we have seen that at n is equal to 0, autocorrelation function value is 1, and in all other places its value will be equal to minus 1 over n. So this line is actually showing minus 1 over n. Again, in the next period, when index value n is equal to capital N, again the autocorrelation value turns out to be 1, and after that it will again equal to minus 1 over n. So this figure basically represents the autocorrelation versus index plot. So one more important property that I want to say at this particular moment is autocorrelation function at n is equal to capital N, or at n is equal to 2n, or n is equal to 3 times of capital N, the value will be plus 1, and in all other places its value will be equal to minus 1 by n. So now I hope you all guys have understood how PN random sequence number would have been generated and its various properties. In case of any doubt, you can ask me in the comment section. So these are the references. Thank you very much for your patient hearing.